Watching this, you are participating in observation. This, on the other hand, is experiment. What is the significance for science of observation and of experiment?
Your powers of observation tell you that heat melts ice. Now, there's a quite commonly believed idea that science is derived from similar observations. From the time of Bacon in the 17th century to John Stuart Mill in the 19th, there are references to the idea that the scientist learns about nature through observation. He is, according to this idea, the observant man with a notebook. He examines natural occurrences, watches for strong or weak appearances of this or that effect, and jots everything down in his notebook. Scientists are a little annoyed by this presentation of their work. Scientific research simply does not follow this pattern. Take, for example, the effect of heat on solids. Well, you saw that heat melts solid ice. You also know that a piece of butter will melt in the heat. But having described these two observations, there is nothing else to draw from them. Actually, heat has an effect on solids much more subtle than that of melting. Only experiment can reveal this process of nature. The experiment might take this form: a metal rod connected to a pointer by means of levers arranged in such a way that any change in the length of the rod will be recorded in a much larger change in the position of the pointer. Now watch me heat the rod. Notice that the pointer is moving. As I keep heating the rod, this pointer is climbing higher and higher. Furthermore, by means of this scale here, I can obtain a numerical value for the expansion of the rod as it is heated. This then is not simple observation of nature. It is experiment. The artificial apparatus revealed information which is vastly more significant than the qualitative observation you gained from the observation of melting. For example, the yield here is not only to show expansion, but to obtain a numerical law connecting expansion with temperature. So it would be barely exaggerating to say that one can never get any science out of pure and simple observation of nature. Observation of nature gives rise to poetry, not to science. Think of the phenomenon of lightning. Few phenomena in nature are more impressive or better calculated to fill man with awe and terror. For centuries, poetry and myth have recorded the emotional echoes of man's utter helplessness in the face of the lightning flash and the all-dreaded thunderstorm. For centuries, then, observation was all. However, some 300 years ago, experimentation with electricity began, though for a long while naturalists saw no connection between lightning and electricity. These early electrical experiments began the creation of small effects such as this. Suppose we have a rod of some non-conducting object like glass or rubber, and we rub it with some material like cat's fur. and then it will be able to attract small pieces of paper, confetti in this case. Then, using much the same friction principle, regular machines were built. You see such an experimental apparatus here. In this case, we don't use rubbing exactly, but rather these metal parts here on the disc are moving opposite metal parts on the disc which is facing me. And the two discs are going to turn if I turn this handle. Now watch the two metal balls on the other side. You can see that a spark is jumping from time to time as I keep turning the handle. This is one of a succession of electrostatic machines designed during the 18th century. There were many smaller, and some were gigantic, capable of generating a discharge which would kill an ox or melt a considerable amount of metal. Reasoning from sparks such as these and from other electric phenomena, Benjamin Franklin speculated that lightning might be a huge electric discharge. He suggested that his ideas be checked experimentally. He proposed that lightning might be silently drawn off thunderclouds by pointed conductors, as he had done with charged bodies in his laboratory. The experiment was almost at once performed in France using the equipment you see here. Here's a contemporary drawing of this equipment. You see here the metal rod with its pointed end that's going to draw electricity, and it's put on wooden poles and isolated from ground by wine bottles, which were apparently conveniently at hand. And as soon as it was tried, the experiment was a huge success. Now, if the observation of lightning yielded the myth of Jupiter hurling his thunderbolt, experimentation, Franklin's experimentation, yielded a clue to its identity. After Franklin, electrical research for more than 100 years abandoned the electrostatic machine for the more profitable field of investigating electric currents, directs and alternating. But in our own time, a demand for very high voltages has prompted the resurrection of the electrostatic machine. This demand stemmed from the need to imitate the high voltages of nature in order to test the automatic devices protecting power lines in a thunderstorm. The demand was also felt in nuclear research, where high voltages are needed to propel electric particles in linear accelerators. This is a model of such a modern electrostatic machine, devised by Professor Van der Graaf of the Massachusetts Institute of Technology. As you can see from this drawing, from this picture, the full scale of Van der Graaf generator is huge, and its discharge is spectacular. Rather than creating its charge by using a hand crank to rotate two plates opposite one another, the Van der Graaf generator employs an electric motor rotating a belt. Here you see a diagram of the apparatus. Here's the electric motor, which turns the belt, and the arrangement yields a very great accumulation of electricity at the top of the generator. In a very short time, this power discharges, and the power of the discharge rivals that of a bolt of lightning. Now, with this small model here, the discharge is, of course, a minute fraction of the power of the full-scale machine. Here I'm going to turn a hand crank again, but this time the hand crank, like in the real Van der Graaf machine, is going to rotate a belt of insulating material. You can see that as I slowly rotate the crank, this belt is moving. And then if I rotate the crank a little faster, you will see a spark jumping between this wire mesh and this ball over there. Watch. This is, of course, just a very small model. Here, then, scientists have built experimental apparatus in order to imitate the power of nature. Studies made with this equipment give insights useful in understanding nuclear particles and in the design of electrical equipment exposed to the actual force of lightning. Observation of lightning itself could never have produced these same insights. Lightning cannot be controlled the way such machine can be controlled, regulated, their forces measured. Such apparatus is very costly. By the way, many people deplore the fact that modern physicists don't seem to be able to discover natural laws anymore by using their hands and simple homemade devices of string and sealing wax. This, after all, was the method used by the 19th century heroes of science. However, the horizons of experimentation have broadened since those days. Today, we investigate forces beyond the imagination of science 100 years ago. For example, those necessary to give to cosmic rays their fantastic velocities. Since nature does use enormous energies in these phenomena, we have no choice but to use the same amount of energy to duplicate them in the laboratory. In order to match and even exceed this power of nature, requires great feats of engineering at the cost of millions of dollars. As for attempting to study these great forces in miniature, scientists are well aware that a certain effect produced at small scale, like here, may not behave in the same way at a larger scale. For instance, a law which is very satisfactory for bodies moving at low speeds is subject to considerable correction in the case of bodies whose velocity approaches the speed of light. In other words, the results of experimentation in physics should never be extrapolated without actual checking. Thus, we have shown that, taking as an example one field of physics, lightning was identified as electricity, not by observation, but by experiment. It is even more remarkable that the whole science of chemistry could not start without a certain piece of experimental equipment. For centuries, medieval alchemists mixed liquids and solids. They worked with intelligence and energy, and they discovered a great deal. But for all that, they missed something very essential. Let us, for example, pour a strong acid on pieces of marble, as they certainly did. So here's marble in small pieces. I put a few pieces here in this jar, and I pour some dilute hydrochloric acid. Any acid would do that anyway. I pour them over this marble, and you can see what happens, a heavy bubbling. Now, what is this bubbling? Is it air that's escaping here, or something else? Well, how can we know if we let it escape? In order to know what causes this bubbling, we ought to be able to collect it. Well, this was not possible until the invention around 1720 of the arrangements that you see here, which was discovered by the Reverend Stephen Hayes. This time we're going to repeat our experiment in this little flask here. And the bubbles, instead of escaping in the air, will be conducted in that glass tube in a bottle. This bottle I fill up with water. I put it upside down, and you will notice that the level of the water stands higher than the level in the tank, like in the experiment of Torricelli. Then here's an indicator dye that I'm going to show you in a moment, and I pour this indicator dye in the water, and it turns it a dark blue. Now, the purpose of this experiment will be to find out whether the gas that escapes is acidic or is basic. And this is what this means. If I put ordinary water in a test tube and a few drops of this dark blue substance, then the dark blue substance is going to remain dark blue as long as the liquid in this tube is acid, but if is basic, but if I pour some acid in it, it's going to turn yellow. Now you know that if I breathe, I take in oxygen and I expire carbon dioxide. Carbon dioxide in dilution with water is going to make an acid. So what? I place this against a piece of white paper, and you see how dark it is? I'm going to blow in this tube. Notice it has changed color instantly and has become perfectly limpid. Actually, it's a light yellow. Now, we're going to repeat the experiment of the bubbling in this flask. We take some marble, put it in the flask, cork it carefully, and I have a funnel there to receive the acid, and I'm going to pour the acid on it, and watch as I pour the acid what happens in the bottle over there. As I pour the acid, instantly the gas is beginning to bubble. Very violently, in fact. Now that my bottle is full of gas, I want to identify that gas. I already found that that gas is acidic because the color of the water has turned. Now I'm going to take some of this gas in the bottle, closing it up with my hand, putting it upside down, and I'm going to pour it over a lighted candle. And look at what happens. I like this little Christmas candle. And I pour this over it, and immediately it's stuffed out. Well, a gas that is acidic, that is heavier than air, so that I can pour it, and that prevents combustion, well, that must be carbon dioxide. So in this way, the collection of gas became possible right after this kind of arrangement had been suggested by Stephen Hayes. The collection of gases revealed an essential point about chemical reactions. That was that whatever elements existed at the beginning of a reaction existed in precisely the same quantities at the end of the reaction, though not in immediately recognizable form. One element, say carbon, may combine with this or that other partner, but its mass never changed. Hundreds of years of observation did not make this discovery possible because a portion of the products of the reaction, the gases, always escaped. But with this experimental setup, it became possible to collect the gases and make this and follow up the element from the beginning to the end of the reaction. Then quickly one gas after another was identified and studied, among them hydrogen, oxygen, and nitrogen, and chemistry got really started. Chemistry gives us another contrast between observation and experimentation. With the newly found concept of the conservation of mass of elements participating in reaction, chemists of the early 19th century found it possible to analyze and describe precisely a great number of the compounds existing in nature. Salt, for example, contains sodium and chlorine. It was sodium chloride, the well-known formula NaCl. Blue stone was copper sulfate, copper, SO4, 5 water. This precise classification and description was the result of chemical analysis. However, very soon, by combining compounds already identified in this way, new compounds came to light, which had never before been observed in nature. Perhaps some were present in nature, but if so, in quantities too small to attract attention. The building up of a chemical compound from its elements is called chemical synthesis. The synthesis of new compounds grew, and it became more and more apparent that many of these elements existed only in the laboratories in which they had been created. Today, the number of known compounds extending to the hundreds of thousands. This enormous field of synthetic compounds developed out of experimentation. The analysis of natural compounds was essentially a form of observation of what existed in nature. But the first 10,000 new compounds, let us say, which the chemist obtained, were the products of experiment in the laboratory. The most important class of natural organic compounds, the proteins, has still to be synthesized, that is, artificially built up. But we should not have to wait very long now, and the consequences will be surely something to watch. Then, again, we are experimenting with the extreme purification of elements and compounds. As chemistry progressed, the proportion of foreign elements remaining as impurities in a given substance has decreased continuously. We're getting more and more pure metals and compounds. But now we're discovering that pure metals have unexpected properties, which only appear when the proportion of impurities has fallen below a level which was unattainable a few years ago. A completely new metallurgy may well result if it were possible to use industrially such very pure metals. Similarly, reliable and long-lived radio tubes could not be made until means had been found to obtain a vacuum much lower than that of the best pumps that 1900 could provide. So here again, you see, it is impossible to extrapolate from ordinary iron to extremely pure iron, or from a high vacuum to the extremely high vacuum of our radio tubes. It may be no exaggeration to suggest that physical science has now almost completely left observation behind her. You can only find observation now at the advanced front of physics, where the physicist is like an explorer penetrating a new territory. There you can find him today observing the behavior of the newer particles, or again the properties of matter at extremely low temperatures. But as soon as the existence of a certain field, such as heat or optics or electrostatics, has been established by observation, the physicist turns to experimentation in order to find out the numerical laws which rule in that particular field. And after these laws have been established, a new era opens in which the physicist or the applied physicist or the engineer uses the new laws and all the old ones in the design of new devices, a steam turbine, an induction motor, a radio transmitter, and the like. These are children of his imagination, which have never before existed in nature, and which he has created to some specific end. We can say the same of most of the hundreds of thousands of compounds created by the organic chemists' ingenious combinations of chains and rings, of which nature has given us the first examples in the distillation products of oil and coal. A complicated linkage of atoms, deliberately contrived by the chemist in order to produce definite clinical effects, is just as much an invention as a television set. In both cases, the individual parts and their functions were known beforehand, but the arrangement and the effect have never been seen. We had begun by remarking that science, the discovery of the laws of nature, was not based upon observation, as is sometimes said, but that physical science is mostly the result of experimentation. We meant to stress the contrast between observation of what nature lays before us, snow melting, plants blossoming, and of the deliberate use of experimentation of the techniques of the laboratory, electrostatic machines, gas collecting tanks, and so forth. But we also noticed historically, observation has to precede experimentation. And following this development, we have unwittingly been led to observe that engineering design follows upon experimental physics, chemical synthesis upon chemical analysis, and in general, applied science upon science proper. Of course, the distinction is often hard or impossible to make, but that is also sometimes the case between observation and experimentation. We have sharpened the contrast today to make our point. This progression from observation of nature to experimentation in the laboratory and to inventions in the technical field seems now a well-established pattern, one that Galileo and Bacon and Descartes in the early 17th century could not very well have foreseen. Even scientists of 50 years ago would probably be much surprised at the transformation of their science, both in extent and in character. We should keep our eyes open and be ready to revise the maps in our old textbooks if we wish to find out our way in this very rapidly changing world.
Two pieces of glass. Put together, they give a revolutionary view of our Earth. And ultimately, of the universe of which Earth is a part. These galaxies, whirling through space 1 million light years distant from our Milky Way. In exploring the large and small of this universe, the dimensions of its galaxies, the size of the cells of its living organisms, science leaves common sense behind. Develops its own logic, its own methods. In weeks to come, witness science and scientists interpreting this universe, its size and its qualities. This is National Educational Television.